Let's look at OChem. We're rocking here. This is going awesome. Okay, let's do Lewis first, and we'll make our way down. Lewis. Okay, I could come up with a random compound and have you draw it. Like that one. That's a fun one. Cool. So there's two ways to do this one. This is what someone was asking me earlier. There's the way I did the earlier problem, which was counting the valence electrons, or the second way is recognizing the functional groups. So let me do it the way I did the first problem. That's the longer way, and then I'll do it the faster way. Okay? So two methods to get to the same answer. Again, I want the Lewis structure. That's what I want. So, valence electrons. There are, how many carbons? 3 carbons. 3 carbons in column 4. There's 1, 2, 3, 4 hydrogens in column 1. And then there's 2 oxygens. I think I got everything. So that's 12 plus 12 plus 4, 30. Now what you do is you write the first, so the carbons are the center of the chain. So you're going to write the first carbon, and then write all the elements around it. 2 H's. H, H. Then you write the next carbon. Then you write the elements around it. H, huh? Oh, did I miscount? Okay, let's see. Oh yeah, 28. Awesome. Thanks. C, and then you write 2 O's around it. O and O. Now, where's the last H going to be? On this carbon or somewhere else? Think about the previous problem. On the oxygen, yeah. If there's a hydrogen connected to an acid, what's the name of this kind of acid? It's a functional group. Carboxylic acid, a COOH is a carboxylic acid. If it's an acid with oxygens, it's going to be on the oxygen, not the other atom. If you drew it here, you would get a messed up Lewis structure. It wouldn't work. Okay, so you're drawing all the skeleton bonds here. Okay, 2, 4, 6, 8, 10, 12, 14, 16. Did I get that right? 2, 4, 6, 8, 10, 12, 14, 16 of 28 total electrons. So now I go to the terminal atoms. All the hydrogens are already filled up. They can only take 1 bond maximum. So now I'll go to the oxygens. Shoot, now I forget again where I was. 16?
Yeah.
Okay, 18, 20, 22. Now I have to go to internal atoms. Oxygens on the inside are my favorite second place to go. 22, I think I said. 20, wait, where was I? 22, 24, 26. And so I have one more set of electrons. I'm 26 of 28. Where do I put that set of electrons? It's not going to go on any of the hydrogens. Will I put it on carbon 1, 2, or 3? They're the only ones it could possibly go on. 1, 2, or 3? I'll just take audience vote. I don't really care. 1? Oh, you care? Or do you want it? No, I don't care. I heard, wait, did you say 1 or 2? 1. Okay, that's cool, whatever. Okay? Okay, let's toss it on there. All right, so now I have a problem. What's my main problem right now? 2 elements, these 2 carbons do not have an octet. So we're going to fix that by making multiple bonds, meaning double or triple bonds. Okay? So what you do is you take a neighboring lone pair, you scratch it out and make a double bond. Take a neighbor, and same thing over here, neighboring lone pair, scratch it out and make a double bond. Now, did that give everything an octet? Yeah. So if everything has an octet, then you have to check formal charges. Do you see anything here, take a look for a moment, that has a non-zero formal charge? Any element that has a formal charge that is not 0. Because we want zeros. Yeah, anybody want me to do any element? They're all zeros. Have a request. Okay, that's cool, easier for me. So, I'll give you a hint. If it's organic and it's neutral, it better have all zeros. Yeah, it would be really weird to find an organic compound that had any non-zeros in it for formal charge. Alright, so that's it, we're done. That's the hard way to do it. If you really want to go for it and this method feels comfortable for you, you need to recognize functional groups. So to have to recognize this is a carboxylic acid. Okay, COOH or O2H is the standard carboxylic acid. And then I have to recognize that as an alkene. Why is that? Because, oops, I'm pointing to something that's not even on the screen. Well, okay, again. That's a carboxylic acid, COOH or CO2H. I have to recognize that as an alkene. The reason is the carbons, based on the number of hydrogens there, there's not 4 single bonds. Like the carbon on the left, you see 2 hydrogens and then a carbon next to it. That's not 4, so better have a double bond there to make that up. So if you recognize that, you can go, without skipping all this garbage and all this right here, you could say, it looks like the first one better be a double bond, and it looks like the second one better be a carboxylic acid. Let's see what happens. Oh, octet, formal charge looks good, done. So that would be the fast way to do it. It takes a little getting used to, but when you get to OChem, most of you will draw them like I just did. Because you'll be able to recognize the functional group pretty fast. If you're hazy on the functional groups, doing it at the second method that I just did will be a lot harder. Yeah? How did I know the left-hand side was alkene? Well, the carbon on the left has 2 hydrogens and then a carbon right next to it. That's 3 atoms, right? But I know every carbon has to have 4 bonds. So I'm like, where's the 4th atom? Doesn't exist, so it better be a double bond. The same is true for the second carbon. It has a carbon on the right and left and a hydrogen. That's only 3 atoms. So to make up for those 3 atoms, it better have a double bond. Yeah. It takes some getting used to. If you get used to it before the test, it's much faster. It's up to you. You don't have to do it this way. Both methods get you obviously to the same answer. One's just a little slower. Okay. So that was Lewis for organic. You do it the same way you've done everything else. That's totally fine. Let's do some hybridization and some functional groups. We'll do those together, and then we'll pause the general topics part of the review. Okay. What if I'll just draw a crazy molecule and we'll do hybridization and functional groups together. Yes. Ooh, that's ugly. Oh, I want to put an oxygen right here. Sorry. I wanted to make it a little uglier. Okay. We won't do every atom per se, but just for fun. Let's do the functional groups first, and then we'll talk about hybridization. So what I want to do, when I do functional groups, here's my style, if I were you. I'd look for carbonyls first. If you forgot what a carbonyl is, let's do a quick review. Carbonyl is something that would look like this. A C double bond O. That's what I would look for first, because if you see a carbonyl, and then that forces a certain type of functional group. Okay, so let's take a look. So I see a carbonyl right here. So that once I see a carbonyl, then I want to know, let me put a big dot. See this carbon that's bonded, double bonded to the O? I need to look what is directly bonded to that carbon that's double bonded to the oxygen. That will determine the functional group. So that carbon in my picture, where I have my pen, is bonded up to a carbon on the top and down low to an oxygen. Okay, so I have a carbonyl bonded to an oxygen. That gives me two possible choices. When a carbonyl has an oxygen on it, it's either which two? An ester or a carboxylic acid. To be a carboxylic acid, what has to be on the oxygen? An H. That's not true here. To be an ester, oxygen has another carbon on it, which is true here. This oxygen has another carbon on it. So right there we have an ester. Let me circle it. This thing here is an ester. Okay. Now I look for other carbonyls. There's one right here. I look what's attached to it. On the top, it's attached to a carbon in a ring. Down below, it's attached to another carbon. So I've got a carbon on either side. What is this called? Not an aldehyde. Ketone. That one's a ketone. If it has a carbon on either side of the carbonyl, it's considered a ketone. Okay, then that's all the carbonyls. Now I go to kind of unusual looking atoms, meaning atoms that are not carbon. This is just my style. So I go to this one. If the nitrogen, there's two possible nitrogen functional groups that you know. If the nitrogen is next to a carbonyl, meaning literally bonded to it, then we call it a what? Amide. But see how there's a carbon in between the nitrogen and the carbonyl? There's this carbon right here. So it's not an amide because of that carbon right there. So a nitrogen not touching a carbonyl is called what? An amine. Yeah, like ammonia, for example. So that is an amine. All right, now I find this one. Here's another thing that's not a carbon. It's an OH. An OH, if you ever see it, has two possibilities. It's either an alcohol or carboxylic acid if it has a carbonyl. But there's no carbonyl here. Oh, there's a third choice. What's the third choice? A phenol. So OH would have actually three choices. So now you have to decide that there's no carbonyl, so it's not a carboxylic acid. Is this a phenol or is this an alcohol? To be a phenol, you need alternating double and single bonds. We've got double, single, double, single. Oh, single, single. There's three singles in a row here. You need a double bond right there for that to count as a phenol. Or also what would count if you had a double bond right here? That would work. But there's no double bond there, so it doesn't work. So this is now an alcohol. Again, to be a phenol, you need a ring with alternating double and single bonds in the ring. This has double, single, single, single. This doesn't count, it'd need to be right here. This would count, yeah, because this could have a resonance structure where this goes here and this jumps somewhere else. So that could work. That's a weird one. Sorry, I shouldn't even said it. Never mind, pretend I didn't say that. Okay. Next year. But yeah, that could count. Yeah, for you, alternate with it. Yeah, okay, forget that. I was getting too excited. Okay, then the other weird thing I see is the oxygen. So it's not a carbon. Yeah, anything else that's not a carbon. I see that oxygen. That oxygen is surrounded by two carbons on top and bottom. So we call that an ether. Okay, then I look for anything else. So are there any unaccounted double or triple bonds? So we see several double bonds. I have to myself, are any of those double bonds making an aromatic? So are there any arenes present? Yes or no? No, you need alternating double and single bonds. So we won't call it aromatic. What will we call all these things? Alkene. Alkene. Okay. All right. Any questions on that? Does an amine have to have 2 hydrogens? No, not necessarily. So an amine, well, this is ammonia. An amine could be this, or R prime, 2 R groups on it. That's an amine. Or it could have 3 R groups on it. Those are all amines. So it doesn't matter the number of hydrogens or the number of carbon groups. I know in the original example it just showed you 1, but R groups and H's can be interchangeable. Amines. Good, glad you asked. Okay, let's do a little bit of hybridization. I'll just point to a carbon, and you can tell me the hybridization. How about that one right there? Yeah, you see 3 groups, 2 single bonds and a double bond, so that would be sp2. How about that one right there? That would be sp3, that's right. Where's the 4th group? It's an undrawn hydrogen, because every carbon has 4 bonds. So make sure you put that hydrogen in there. There's a secret hydrogen, so that would be 4, so that's sp3. Let's do that one right there. That nitrogen right there. sp3, where's the 4th group? It's an invisible lone pair I haven't drawn in because I didn't want to waste that ink, but now I did. Okay, that's sp3. How about that carbon right there on the end? sp3, that's right, because there's 3 undrawn hydrogens. So that's an sp3, 4 groups, etc. Okay? By the way, let's do oxygen just to get everything warmed up. That oxygen would be sp3. Where's the other 2 groups? There's 2 lone pairs. 1 and then 2. So that oxygen and then the ether oxygen are both sp3. Okay, so the ester and the ether oxygen are both sp3. All right, I think what we'll do is pause right there. We went over your list. Everybody who needs to leave and watch Monaco or whatever tonight, go for it. The rest of you just stay in your seats, and I'll take it by raising my hand.